Okay, so now we're going to talk about what a line spectra is and how that relates to the Bohr model of the atom, at least a little bit. Um, so what we're looking at here is to really understand the background for line spectra, we have to understand a little bit about white light and what we know about white light. And so if we look at our diagram over here, which you can't see my hand like a magician all of a sudden, full white light is actually composed of all the possible wavelengths of the visible spectrum. And so because all possible pieces of the visible spectrum are present in white light, if we take white light and we pass it through a glass prism, it's going to spread all of those lights out, all of that light out into its different wavelengths of light. And we're going to see the full spectrum there from red all the way back down to violet. Now, just like raindrops make a rainbow. It's the same process, okay? Now, this is a continuous spectrum because that means that the light is continuous from this one point of the visible spectrum all the way down to the other side of the visible spectrum. And so that's what a continuous spectrum would be referencing. And so I'm off the page. Oops. Okay. Now, but not all light contains all the wavelengths of visible light. And so if the light is not a continuous, is passed through a prism, words. If light that does not contain all of this different spectrum of light is passed through a prism, we get an entirely different looking spectrum. And so that's what this is right here. Okay, what we're looking at here, this is actually hydrogen light. And so this is hydrogen gas inside this tube. And it's getting heated up a whole bunch with electrical charges, and it's creating light. That light is passing through a prism here, and it's spreading what little bands of light there are, and it's spreading them all out into their 4 different spots so that we can see where they are. And so now here on the bottom we can see 410, 430, 456, and I believe that is 656.2. Okay, so those are the different lines that get emitted from a hydrogen atom. Now, this is a line spectrum, and so we're going to write that here. So that's a line spectra. And so a line, not alive, a line spectra. So here you go. This is a line spectrum. Because all of the lights is given out to us in vertical little lines. Okay. Now, the reason that this works is because this is the light that's there. There's nothing else there. And so because there's nothing else there, we can spread that light out into its different sources, and we can see those visible little lines in different spots, and that is going to tell us what's going on and how it works. Now, what's really cool about this is we can do this with all kinds of different light. Okay? And I think I missed one. Where did I miss that? You can see 4 distinct lines. Oh, I missed it right here. Sorry. There's supposed to be a 4 in the blank right there. So there are 4 distinct lines after the light passes through the prism. And so, there we go. Now, let me erase all of this stuff so it's not in the way. Okay. So now, every element has and every element, and thus every compound, has these characteristic line spectrums that can be used to identify what's there. And this is what astronomers are doing when they look at stars in space to try and figure out what's burning inside that star. And so it's kind of cool, actually. It's a really neat way to identify elements based on the light that they produce when those atoms are excited. Now, the question that you have to ask is why? And so the simple explanation is that each of these colored lines correlates to an amount of energy that is released when an electron in an excited state loses energy and falls back to its ground state configuration. So I want to spend a second talking about excited state because I didn't do it in the notes very well here. Okay, so we're going to go over here and I'm going to show you we've got a diagram right here, but I'm going to leave that one alone because I don't want to mess it up. Okay, so here's my nucleus. Okay, I've got some positively charged electrons or positively charged protons and a couple of neutrons in there. And here's an energy level. And here's an energy level, and here's an energy level. Okay? Now, doesn't matter what atom it is. So let's say I've got an electron chilling out right here. Okay? And let's say that I take this atom, or a whole bunch of these atoms, and I zap it with some energy. Okay, I either hit it with electricity or I hit it with heat from a Bunsen burner, a torch, whatever, it doesn't matter. All this atom can do with that energy, other than shaking and vibrating in place, is it can take that energy from that electron, and if it's the right level of energy, it can pop that electron up into a higher level orbital. So let's say that electron got all excited, and it now spins around out here in this energy level orbital. 1, 2, 3, 4. This is the 4th orbital. Okay? So this electron got promoted from the 1st orbital up to the 4th orbital. Now that electron is going to spin around and spin around and spin around out in that area until the electron says, all right, this is like work. I'm kind of done with this. I don't want to do this anymore. I'm going to drop back down. And so when it does that, it drops back down to where it came from. Okay, where it started. That's what we call its ground state. Now, as soon as it does that, though, this atom releases that change in energy. So that energy gets released out in the form of visible light. And so there's a wave of visible light getting released because of that electron transition back down. Now, this energy, we can characterize this energy using Planck's law. And so we could figure out how much energy it requires to get from this spot to this spot. And that's exactly what we're talking about here. Okay? Now, this is a hydrogen atom over here in the diagram to your right. Okay? And so you can see right here, this is where we have our nanometers labeled here. We have 656, 496, 434, and 410. And so this is the energy of those transitions. From the lowest energy level to the next, from the lowest to the 3rd, from the lowest to the 4th, lowest to the 5th. And each of those transitions has its own energy level. Now, this is called the Balmer series because Balmer was the dude's name, and it's not going to let me show you that anyway, so that's funny. So that's the Balmer series. Now, what's really crazy about this happens in other spectrums of light. So the Lyman series happens in a non-visible portion of the electromagnetic spectrum, and so does the Paschen series happen in the non-visible portion of the electromagnetic spectrum. And so if we looked at this in ultraviolet or infrared or some of those other things, those other portions of the electromagnetic spectrum, we would see other lines in it as well. And so hydrogen's not the only atom that does this. There's whole bunches of atoms. So every atom does this. And every atom has a couple of different series of these that fit in different spots. And so that's what's really cool about this, is we can see this in a whole bunch of different places in the electromagnetic spectrum. And so, yeah. Now, the one thing about this that is super, super, super important is that in order to make that electronic transition, the energy has to be exactly precisely the right energy to jump from this spot to this spot, okay, or this spot to this spot. If it doesn't have exactly that right threshold, it's not going to make the jump. If it isn't high enough, it can't make it. If it's too high, it can't make it. So it has to be at exactly the right level of energy to make the transition from here to here. There's an analogy that I'm going to share with you in class, but we'll talk about that in class. So that's it. That's all I wanted to talk about in terms of the line spectra. We have a lab that we're going to work on using this, and you'll get to see firsthand how this plays out. So see you soon. Bye.